So first, let me put again on board 3 theorems, and our goal today would be to prove these theorems. Up to some black boxes that we don't have theory to fill in. Okay, so theorem 1 says the following. So let me have a connected Lie group G. And then I have 2 sets. One of them is connected virtual Lie subgroups of G, and another set is Lie subalgebras of the Lie algebra of G capital, which we denote by G small. And we have we can construct map from here to here, take a group, and consider its tangent space at identity. So the statement is that this map, okay, so the map is a bijection. Theorem 2 establishes another bijection. But for that, I need to take G to be connected, simply connected. Lie group. And the map that we claim that it is a bijection, it's, well, I would like this to be G1, I have G2 some other Lie group, and I have all homomorphisms from G1 to G2, and map to all homomorphisms between corresponding Lie algebras, and the correspondence is just take homomorphism and compute it differential at identity. Okay, and again, then the map is a bijection. Okay, and I have third theorem that says that, maybe I can fit it in here. Theorem 3 says that for any finite dimensional Lie algebra G, there exists unique connected, simply connected group, Lie group G tilde, such that Lie of G tilde is G. So Lie algebra of G tilde is G. And also there is another another part of this, which is that every, it's kind of obvious that after that is that every every Lie group with this Lie algebra is a quotient of G tilde by some discrete subgroup. Okay, I don't want to spend I'm going to remind it in any case. So here is our three theorems, and so what will be the logistics of our proofs? So theorem 1 will take most of time today. Okay, and so we will leave it for the second half of the lecture. Okay, theorem 2. Let us show first that theorem 2 follows from theorem 1. Okay, so first proposition. Theorem 2 follows from theorem 1. Okay, proof. All right, so what should we take? We should take some homomorphism between Lie algebras and construct homomorphism between Lie groups such that its differential is what we started with. And we know that, first of all, in theorem 2, we know injectivity, right? Because G1 is connected. And we proved last time that if the map homomorphism from connected Lie group is defined by its differential at identity. Right? So injectivity we know, so we need to prove surjectivity. And again, that means that, okay, let me take some f from here. And let me consider the following subspace of G1 plus G2. So it is what's called graph of this function. So it's a set of all pairs like this, and where x lives in G1, right? So this thing lives in G1 plus G2 subset. It is also a vector subspace, and it is also Lie subalgebra, because F is homomorphism of Lie algebras. So since F is homomorphism of Lie algebras, H is a Lie subalgebra of G. Okay. Well, you can already guess where it goes, right? Since we have subalgebra in here, so we can find corresponding virtual connected Lie subgroup in G1 times G2. Right. So let by theorem 1 there exists H virtual connected Li subgroup of G1 times G2 such that the Li subalgebra of H is H. Okay. Very well. Let me. So I have G1 times G2, and I can consider projections to first component to second component. So let P1, P2 denote projections from G1, G2 to either G1 or G2 respectively. Then let me consider the following map. Okay, so I also have an inclusion map H to G1 times G2, right? So it's inclusion. So now I'm going to consider this map R. It is composition of I first, and then so I goes from H to here, and then I project to G1. So then P1. All right, so this map is from H to G1. Okay, so then what is differential of R? Differential of R is from H to G, from H small to G1 small, right? And it should take H small is like it's something like this, right? So dr is composition of di and dp1. Okay, so what it does, it takes an element like this x, f of x. Then di that just does nothing. It just considers as a parent here, right? And then p1 just takes x, right? So this map is just x, f of x goes to x. So what we need from that is that dr is actually right. So dr here, I would so it is actually injective. So it is injective. Okay. Also, it is well, it is injective and it is surjective as well, right? So it's actually bijective, I can say. So dr is a linear isomorphism. Okay. So actually surjective as well, right? I can take any x from dg1 here, right, and obtain any x in dg1 like that. So dr is an isomorphism. Okay. Also, I claim that R is surjective. So R is surjective. So let me see. So what do? I would like to obtain the whole G1. So I take conclusion. No, I mean, why H is G1? So that's what we would like. So we would like to see that it is a covering map, right? Right. So if we prove that it is, if we see that it is surjective, then actually I know that G1, right, is H quotient by some gamma. So let me finish the statement. So why this question? So I don't see right away why. So let us think about this maybe a bit later. So okay, we would like so if it's surjective, then just by homomorphism theorem, right? G1 is H over gamma, where gamma is a kernel of this, but dr is injective, so therefore kernel has dimension 0, right? So therefore this thing is discrete subgroup of H. But then we need to use that G1 is simply connected. Right. It is. It gives the whole thing. It is surjective because G1 is connected, right? So therefore, right. So it has the same dimension as G1, right? So it's it is an open and closed subset in G1. Right. Yeah. So here for surjectivity, I really need to use the fact that G1 is connected. Okay. I don't know. I'm kind of confused. Why? So I think you need to use that G1 is connected, but okay, let me not spend too much time on that. I should think about this for a minute maybe and comment. If it comes during the proof, then okay, let us comment. We'll mention this. Okay. Okay. So what I would like to so suppose it's surjective. Just to proceed to the proof, we need to use now that G1 is simply connected. Okay, so from the fact that G1 is simply connected, it just means that gamma should be gamma should be just trivial subgroup, right? Because you have so G1, so actually Lie algebras of G1 and H they coincide, right? So therefore G1, since it's simply connected, it is
Can I have a question?
yeah, sure.
We have proved that taking the differential is bijective, right?
Yeah, differential is bijective.
So like can we like compute a surjective, find a surjective map such that it coincides with GR, with the differential of the R?
But why?
To show that it's surjective.
No, the thing is that this should be, I mean, if I have a map, so the thing is that if I have a map, smooth map, right, it maps, so H is something connected in here, right?
Because the differential looks like a projection to the x.
Yeah, it is. It's just projection to the x.
Projection is surjective.
Yeah. So this one is okay. It's surjective, and so you're saying that. I mean, yes, this is surjective, and this is injective. That's for sure. But we need R to be surjective. So that's the whole point. So how do you? I don't know. I don't see it right away. I don't know. Okay. I don't know. So anyways, this will be if you'll not get it during the lecture, this will be something that I should comment later. Okay. Anyways. So now I'm using simply connectedness of G1. So I claim that since G1 is simply connected, right, and G1 H covers G1, yeah. So this is the whole. Right. So G1 is a I don't know. It's kind of trivial, but G1 is universal cover of itself, of course. Right. On the other hand, we say that H is a cover of G1. Right. Maybe I can have this triangle rather like this. But if I have universal cover, right? But then this map exists, right? And then H is G1 quotient by some gamma, I don't know, tilde, right? Because of homomorphism theorems here. In any case, if I have this gamma to be non-trivial group, right? I take G1, right, and take H over gamma, and then after that, so I have after that I can take H to be this G1 over gamma tilde. Right, over gamma. And all these are isomorphisms, right? The only way this to be isomorphic to this is that the gamma is a trivial group. Both gamma tilde and gamma are trivial groups, right? Otherwise, this double this double projection will have some kernel. And so G1 will not be isomorphic to itself, right? So therefore, gamma is just E. So what we proved is that actually H is isomorphic to G1. And R proved up to the statement that R is surjective. And R is an isomorphism. Okay, then I consider the following thing. I take phi to be the following map: P2, I, R inverse. So that's why I needed R to be invertible. So this map is from, this is the map that we need, that we are going to construct, this is our goal, to construct a map whose differential is f. So this is a map from G1 to G2, you can check, right? So this one goes from G1 to H, this includes H into G1 times G2, and then we project to G2. And what is its differential? Okay, dr inverse takes x, right? And then gives me a pair x f of x. I really does nothing in formulas. And then I project to second component. So really d phi is our map f. Right? Okay, so up to this surjectivity, we proved the proposition, right? Okay, let me think for a half of a minute. If I don't get it, should be simple. I don't know. It's because I didn't have my morning coffee. So the whole point, right, that G1 is connected, right, and H is of the same dimension as G1. Right, so we kind of have the whole neighborhood of identity here, but yeah. So if you right, yeah. This. Okay, I got it. I think the whole point is indeed that the surjective means that I take any G1 or G from G1, right? It is, and for sure, I have some neighborhood of identity, right, that lives in the image of R. Right? Just because differential is an isomorphism, and I don't know, by inverse function theorem or something like this, it's a local diffeomorphism actually, right? So, and also R is a homomorphism of groups, right? So I take G, so G is written as G1 and so on, GK, right? Maybe with inverses. So each of these does have pre-image under R, right? So I can take H1. There exists H1, Hk, right, such that R of H I is Gi, right? Then I take H to be H1, maybe inverse H2, maybe inverse, I don't know, Hk. So I claim that this is preimage of G, arbitrarily chosen, under R, right? Because R is a homomorphism of groups. So this proves that it's surjective. Okay? Okay, very well. All right, so let's move on then. Next stage would be to prove prove theorem 3 from theorem 1 and some other theorem which is called Edo's theorem. It says that every finite dimensional Li algebra G, well, actually over maybe real, maybe complex. It works for both. Is as Li subalgebra of GLN K for some n. Okay, this is a very strong theorem, right? It says that every Lie algebra, every finite dimensional Lie algebra is a matrix Lie algebra. This is not true for Lie groups, just should mention right away. There are Lie groups which are not subgroups of GLN. And maybe we'll see some examples, but for Lie algebras it's true. Right. We're not going to prove it. We're just not ready. One needs a lot of structure theory of Lie algebras to prove it. So maybe further in the course I can comment when we'll be ready, know all the notions. But for example, it follows not easily from what's called Levy's decomposition, right? Which says that every Lie algebra is semi-direct sum of its radical, which is maximal solvable, and semi-simple Lie algebra, right? And but again, so for the proof of this. You may, for example, if you are very interested and don't want to wait until we know all the structure theory, it's, for example, in Fulton-Harris. I think it's written in appendix there, and the proof there is it's good proof that's understandable. Okay. We rather would just mention, so let me put it as a remark, that Edo theorem is clear for Lie algebras without center. So if G has no center, what does it mean? So center of G, these are all elements X and G, such that they commute with any Y in G. And node center means that this is just 0.
Then you can use adjoint.
Yes, exactly. Okay, so how to put it? The right word is that joint representation is faithful. It has no kernel. So then, so then add. So it's a homomorphism of which Lie groups? G to GLG, right? Which is the same as GLN, where n is dimension of G, right? I should say like this, maybe. So then this has no kernel. Right? Because the kernel of this is exactly the center of Lie algebra G. And it means that G is a subalgebra in GLN where n is dimension of G. Right? So Edo theorem false. And this will be actually will be enough almost for all examples that we'll see, because we'll work a lot with semi-simple Lie algebras, and they don't have center. So all this hard stuff like Levi decomposition is it's where you have center, right, and you need first to construct a faithful representation of the center, and then extend it to representation of G that is faithful in center. That's how it's proved. Okay, so this is about Edo theorem. Next, we're going to use it, and first theorem, and actually, I don't know, second, everything, to prove the third theorem. Theorem 1 and theorem 1, well, we'll use theorem 2 as well, but since theorem 1 implies theorem 2, I will not use theorem 1 and Edo theorem imply theorem 3. Okay, once you know this, it's pretty easy, right? Because so proof of proposition. Okay, you know that G is a subalgebra of GLG, right? So by Edo, G is subalgebra of GLG. So again, theorem 3 says what? If you give me any finite-dimensional Lie algebra, there exists unique simply connected Lie group with this Lie algebra. And moreover, every connected is a quotient of this simply connected. Every connected with this Lie algebra. So this is the G that you gave me. Okay, I'm going to construct, first I'm going to construct some connected Lie algebra with this Lie group with this Lie algebra. How to do this? Again, this is subalgebra in here, so therefore by theorem 1, there exists G, which is subgroup right? In where? In GLG. It's a connected virtual subgroup of this, right? So therefore, connected. So therefore we found some. So it is connected. So there exists this such that TEG equals to G. So we found some connected Lie group with this Lie algebra. But then consider G tilde, which is universal cover of G, right? And this will so G tilde has also Lie algebra G, right? Because projection map from G tilde to G, it is a covering map, right? So therefore, its kernel is some discrete thing, right? So therefore, the tangent space to kernel is just 0, right? So differential has no kernel. So it means that Lie algebra of G tilde is isomorphic to Lie algebra of G. Okay, so we constructed some connected, simply connected now with this Lie algebra. Well, the fact that it is unique, it's pretty simple. That's where we maybe use theorem 2. Okay, uniqueness of G tilde. So suppose G is some other Lie group which is connected, simply connected well, with Lie algebra G, right? So consider just identity map, right? From G to G, it lives in here, right? By theorem 2 now, I can, so this is Lie algebra both for G tilde and for G hat, right? So therefore I can, there exists some map, I don't know, phi, homomorphism, and it is from G tilde to G hat, right? Such that, well, d phi is just identity, right? So again, d phi is identity. This map. So this is map between simply connected spaces with which is local diffeomorphism. This means that it is actual well, isomorphism, right? By the same argument as in proving theorem 1, theorem 2 from theorem 1, right? So again, we have so d phi is identity, phi should be surjective for the same reason as what I was suffering to do, right? And so therefore, G tilde is G hat over some gamma, right? But G tilde, so this is by the same argument as in the proof of theorem 2. And G tilde, then the G tilde is simply connected. And this means that, again, gamma is just trivial. And again, this is, again, the same argument that we gave there.
So gamma is P1 group.
Yeah, well, actually, yes, but we didn't check it.
Yeah.
Yeah, you can use seminar problem if you wish here. Okay. Very well. So this means what? That I have an G tilde is isomorphic to G hat, so it's a uniqueness now. And then any, so if G is finally is connected such that its Li algebra is G, well, you just consider, again, its universal cover, right? This will be connected, simply connected with this Li algebra G, right? So therefore, and because of uniqueness, it will coincide with G tilde, right? So then G tilde is the universal cover of G, and so therefore G is G tilde over gamma, for some gamma, discrete. Okay, so we proved all the statements in theorem 3. They actually, so the hard part is Edo theorem and theorem 1. Okay, any questions? Do you guys follow at all?
Yes.
Okay. Adriana, so where did you lost?
Just at the end, I was just kind of lost. But
Uh,
maybe, I think I need to read by myself just to get everything clear. So we can continue.
Okay. All right. So let's now do. So Ada theorem is hard part that we will not do today. So let's try to do the hard part, which is theorem 1. But again, for theorem 1, I will need what's called Campbell-Hausdorff series. So let's formulate it as theorem. This theorem let us call uniqueness of should be not uniqueness but rather existence. Sorry, existence of Campbell-Hausdorff series. It says the following: for sufficiently small x and y, define well, the series, should say a series well, in X and Y. So these are elements in G, right? Small means they're close enough to 0, right? It's just topology of, I don't know, vector space. Z, X, Y. So this series in X and Y. By so I should rather maybe not a series, but let me just say define a function for starters. In X and Y, such that, well, e to the x, e to the y is e to the z xy. Right? Exponential map is diffeomorphism for some neighborhood of identity and neighborhood of 0. Right? So therefore, for small enough x and y, I can define such a map. Right? I can invert exponential. Okay. So then the statement is the following. Then the Taylor expansion of zxy, the function of x and y, is a Li series. So what does it mean? So that is z of x, y is a series of this sort. So I take the bracket of x, y, and then apply some number of x's of commutators. So it all consists of commutators. So that's what it means to be Li series, right? It is sum, maybe some infinite sum of terms that consist of commutators of this sort. So I take some number of commutators with x, then some number of commutators. So x. Then some number of commutators with y. And so on. And so this is sum of such things, maybe with some coefficients. Okay?
And on what is summation, x and y?
No. X and y are fixed. So with sum over it's just there's no indexes as it is in here. Well, I here I'm just explaining what is Li series. So Li series is an infinite sum of terms of such sorts. Okay.
So there can be any sequence of x and y.
Yes. So basically, I'm just fixing length of the word like in integers, right? And then I will have first like r1 x's, then r2 y's, then r3 x's, and so on. And then I sum over all ri, if you want more formalism here, right? It can be all written down. Okay, so we will try to prove this. If not today, then next time. But to prove theorem 1 accurately, I will need this. So proof of theorem 1. Okay, so let's recall what was theorem 1. Theorem 1 says that if you give me subalgebra in Lie algebra, that I give you connected virtual Lie subgroup with Lie algebra corresponding to this Lie subalgebra. Okay. So consider the subalgebra that you gave me. So this is a Lie subalgebra of G. And then you do something very natural, right? What would you think? So how do I create H inside capital inside G capital? What do you think? Well, yeah, exponential. Yeah, so you take exponential, and then which gives you something. You don't know, maybe it's a group or whatever. You just take exponential. It might not be a group, as we see with SLN, for example. Right? But then I just take this something that I have by in the image and generate a subgroup by it. And I claim that this subgroup is what I need, but I need to introduce Lie group structure there. So take H to be the subgroup. This is just some abstract subgroup of G generated by exp H. Right? So this exp is exp for G. Right? So it's an image of some subset of this. Okay? Very well. I would like it to be manifold, right? And I cannot use induced topology because it might be virtual Lie subgroup, right? So I should be more accurate here. So let me choose V, neighborhood of 0, right? 0 is in here. Such that, well, my exponential map from V to U, which is image of V under exponential map, is, well, diffeo. Okay, so I can of course take first like some. U is just image of this exponential under this exponential of this V that I chose. Yeah. So right, exponential is a locally diffeomorphism between neighborhood of identity of G and neighborhood of 0, right? But I can restrict it to intersection of this local neighborhood around 0 here with H, right? It will be diffeomorphism from this intersection of this neighborhood with H, which is V, to U. Okay, and then I define topology on where? On H as follows. I just give you the base of topology. So the base is H times W for every H and H, and W is an open subset in U. Okay. So this is a base of topology. So by definition, your open sets are all unions of this. Then I need a bunch of observations. So first of all, H becomes a Hausdorff space with this topology. This is an easy exercise at me. Second, I claim that H is, of course, I would like it to be second countable, right? This is a bit less easy exercise. But okay, let me actually do it, because when I was preparing for the lecture, I was not able to do it like right away. So maybe you will not be able to do it. This one is really easy. I'm not lying to you. Okay, so what's the second countable means that it has countable base. So far as this one is not countable. All right. So proof of this, of 2. The thing is that U, right, it's actually a submanifold in G, right, with just one chart, this one, right? So as a manifold, it's this, topologically, this is just some open connected neighborhood of, maybe not even connected, I don't know, I don't care, of 0 in some k, in some kn or rn, right? So topologically, such a nice space is what's called separable. So it has dense countable subset. Right? You just can take, intersection of this with just all points with rational coordinates, right? All right. So let me denote this countable set as Hi. This is countable base. Countable dense subset of U.
Again, why it exists?
Because just U is a piece of Rn. Just take its intersection with all. Just take all points here with rational coordinates. Okay, then U. Again, it's a manifold, so it's second countable. So I can take Ui to be a countable base of U. And then
So exponent is an open map.
Exponential is it's locally diffuse. It's locally open, of course. I just need locally here. Everything. Okay. So then I take another GI. So this is set of all finite products of elements from Hi. So this set, if you think a little bit, it's also countable. right? You just need to fix length first, and then all words with this length, and so this will be a product of two countable sets. But then I claim that GI UJ, this is countable base in U, is a base, countable base of topology on H. So that's it. Okay, this is some fun with topology. Usually, if you skip this, nobody notices. But but I try to be as honest as possible. All right. So this is number 2. Some reason I skipped 3, but okay. So I have. I would like it to be manifold, so I need some charts, right? So for any H in H, so chart is what you expect. We have charts. So your neighborhood of H is this one. And then chart is that you first shift it to U by left multiplication by H inverse, and then apply X inverse. And this gives you back to V. Okay. So this charts they actually smooth because well, because this is smooth, right, in topology of G, but locally your H is submanifold of G, so therefore this gives you smooth atlas. So 3, so 1, 2, 3. Third observation is that H is manifold, and by construction it is immersed submanifold of G. Okay. Well, it's a manifold. You have inclusion map, and inclusion map is locally a diffeomorphism. So that's why it's an immersed submanifold. All right. What else do we? So right now I would like to attract your attention to. So I might just stop here because okay, I have immersed submanifold, and I have it is a subgroup, right? So I think the definition that I gave you, so when I checked my notes, it might be some mistaken definition of virtual Lie group, virtual Lie subgroup. So and this slight inaccuracy didn't play too much until now, so that's why I noticed it only now. So you should check your notes, but maybe I said that virtual Lie subgroup, it should be first, well, subgroup H of G, right? It should be first H is just abstract subgroup, and 2H is an immersed submanifold.
Yes, that wasn't.
Yeah, so this is not correct. I'm again. This is not correct. You should correct it as because this is if it's just an immersed submanifold, it is very not clear that H is a Lie group at all. The multiplication is that multiplication is continuous is not clear at all, right? If you don't have an induced topology, but in this case you don't have induced topology, right? So what should I do? So I should say that H is a Lie group such that you have inclusion map is a homomorphism, so I should say injective injective homomorphism of Lie groups. Then this is much better because we have from the beginning Lie group structure on H something, and then you include it into G, and the corresponding map should be injective immersion, and also should be homomorphism of Lie groups. Okay. So I should not stop here, but rather I should see that H is a Lie group itself. Okay, it has multiplication already, so I should check that this multiplication is smooth. Inversion is also can be the smoothness of inversion can be checked similarly, or sometimes I don't know if you check or not that smoothness of multiplication is actually enough to check that something is a Lie group. Anyways, so what we should say is that number 4 is that H is a Lie group. Why is this true? So that's where we will need Campbell-Hausdorff series. So I need to check that so I have multiplication, right? It's from H times H to H. So let me now take small enough neighborhood. So your Campbell-Hausdorff series is Taylor series, so it converges at a small enough neighborhood of 0, right? So let V tilde be the neighborhood of 0 in G such that the Campbell-Hausdorff series converges. Then let me consider, so this is something small, well, okay. So anyways, let me now consider VH tilde, which is just intersection of V tilde with H. Right, so this is something inside V that we chose in H. Right? Okay. Then let me take multiplication, but first precompose it with exp inverse times exp inverse, and then compose it with exp. So yeah,
Maybe before we continue in 3, we say that we have an immersion by construction.
Yes.
But why it is not, say, an embedding? Why we are requiring this condition?
Well, because you know only local. Your locally you have. So again, you know that what. So your here's your H, right? And at some point H, your neighborhood of this point, right, is just a slice of a neighborhood of maybe some chart in G, right, by Kn, right? But you don't. But this is locally for H, right? So it might happen that you actually in this thing you have like a infinitely many these things, like this, right? Very, very, very close. And in induced topology, you will have, take preimage of all of those, like in a tensed torus winding. Okay. So when you generated a group, you created a monster in a sense of topology, right? It might happen. Well, not such a big monster, but I mean, it's a virtual Lie group, not this submanifold. Okay, so this one goes from VH tilde times. So I consider its restriction to VH tilde times VH tilde. So and then I take VH tilde times VH tilde. And so where it goes? And that's where I need Campbell-Hausdorff. Because Campbell-Hausdorff says that I can find exponential, this will be exponential of Lie series. But Lie series contains only commutators. So when taking commutators of x and y, you will never go outside of H, right? So you actually live in V. So remember, V was in this H such that exponential map gave me diffeomorphism. Okay? So without the Campbell-Hausdorff series, I don't know if I get here. So let me maybe draw a picture again. So I have some neighborhood of identity in G, and I have V, which is inside H, right? So H is my thing, this, like a plane, whatever. And I take, so V tilde is something little bit smaller, so that Campbell-Hausdorff will work, right? So I take 2 points in here, pretty close ones. And Campbell-Hausdorff says that I'm still in this slice. I don't go somewhere outside, right? So this is X, I don't know, this is G1, G2, and this is M of G1, G2, or just G1 times G2, right? So this doesn't happen. G1 times G2, if they are close enough, it's still in this slice. So, and this is my V, right? I don't go outside of V. And so the whole point is that this thing now is a chart of H, right? If we will go outside, we might have no chart, to check smoothness. That's the whole point. But this thing, so this restricted to VH tilde times VH tilde, right? But this thing, it's smooth as restriction of a smooth map. Okay? All right. So some accuracy needed here. So for example, I don't know, in some books people just skip it. But all right. So this gives me continuity, smoothness of multiplication, right? So therefore, M is smooth. So I checked smoothness around identity. Well, by shifting by left actions, I can check smoothness in other points, right? M is smooth. All right. So inversion, right, is smooth by the same argument. Actually easier because it just X in a Lie group algebra, inversion just means taking minus sign, right? You don't even need a Campbell-Hausdorff here, right? So inversion is smooth by the same argument, but even you don't need Campbell-Hausdorff. Okay, and then it means that H is a Lie group. So we convinced ourselves in statement 4. And statement 5 is that, well, so what do we need from H? That it's Lie algebra is the Lie algebra H small that we started with, right? So 6 is that TEH is H. But indeed, for every, so indeed,
Where is H?
hmm?
Where was number 5? Yeah, 4.
Before, I don't know. But I think in my notes it's 7 already, so 5. So indeed, we have what for every y in H, right? Exp ty is in H for any t, right? By construction. So therefore, d over dt exp t y, so tangent vector to this curve at 0, it belongs to TEH because of this, right? But tangent vector to this curve is y, right? So therefore y belongs to TEH. So it means that H, so this thing is actually y, right? So therefore it means that H is inside TEH, but we figured that dimension of H and dimension of H small are the same. So dimension of H equals to dimension of H capital, so therefore H equals TH. Okay, and finally 6 is that H is connected Lie group. Why is that true?
Exponent is subjective.
No, not really.
Since we
Yes.
generated it by
Neighborhood of identity should be connected, right? Otherwise, if it was not connected, right, the neighborhood of identity would generate just connected component of identity, not the whole group. So H is connected because it is generated by neighborhood, by its neighborhood of, and I should say connected even, right, or of identity. So that's it. We proved up to Campbell-Hausdorff, we proved theorem 1, right?
In term 5, why the exponential of dy was in H?
Because y is in H, ty is in H, right?
Yeah,
So we took image of H
yeah.
to generate it.